Good morning, everyone. Today, I'm going to present a paper, Debiasing model updates for improving personalized federated training. And the authors are from Boston University and the ARM Machine Learning Research Lab. And this paper is accepted by ICML this year. So before we go through the details, let's recap the federated learning. In federated learning, there are a central server and M devices or nodes. So the goal of the federated learning is to solve the following distributed optimization problem. Here, the server will maintain a server model W, and the optimization problem is to find the optimal server model that can minimize the average of local losses. So the classic federated learning method to solve this problem is that at each communication round, each device will update the server model downloaded from the server towards minimizing the local loss, and then send the updated model to the server. And the server will then aggregate all the local models as the new server model. And this process will iterate until converge. One of the main challenge of federated learning is that the local data sets are heterogeneous. That is, different devices will have different classes of data. For example, in the image recognition setting here, the device one is only interested in vehicles, so the device one only has images of airplanes and automobiles, and device two is interested in animals, so this device only has the images of birds and cats. But as I mentioned before, the federated learning aims to train a general model that captures the general knowledge of all local data sets, which is lack of personalization when we apply the general nerd model locally to do predictions. So this work focuses on the problem of achieving personalization of federated learning. So the general idea here is to train a meta model, which captures the general information of the distributed data sets, and then each device, so this is a meta model, and then each device transform this meta model using the transform function TI to personalize this meta model to its own local model using their own local data sets. So when you use this personalized model for prediction on device, the prediction results can be more accurate. So this is a general formulation of the personalized federated learning. So now the goal becomes to find a good meta model that can minimize the average loss on local personalized models. More precisely, and each communication round, the server will transmit the meta model W to all the devices, and the device I will update the meta model W using its own loss function Fi and its adaptation function Ti, and get the new local model Wi. And then it transmits the updated model Wi to the server, and the server will aggregate all these local models to update the meta model. And this iterate will continue until converge. So before we go to more details, let's look at the prior work. So the most related work is the MAML personalization, which is to rapidly fine-tune the meta model with device data by taking one step of local gradient descent on the local loss. The MAML is built up on the fit average algorithm, which is a classic algorithm for solving the federated learning problems. And I mentioned before, and each round of the federated learning of fit average, the devices will take multiple steps of SGD to update the server model. And then the server will aggregate these devices models to update the server model. And this process continue many rounds until converge. However, if we use fit average, if the local losses are different, then the local model update will be biased towards local minimal, not the global minimal, because the goal of the federated learning is to find out the global minimal. So there exists a bias. And also the convergence of the fit average depends on the IID condition, that is the heterogeneity level of local data sets. And if we have heterogeneous data sets, then different devices will have different local data distributions, which will result in poor performance of the fit average. And in practice, data are usually heterogeneous because users have different preferences and habits. So let's look at what is the bias here. For example, assume we have 5 devices. So here, 1, 2, 3, 4, 5. The global minimal is the black circle, and all this colorful circle represents the local minimal of different devices. And assume our current meta model to be trained is here, and assume devices become active one by one, which means at each communication round, only one device is active. So for example, here, at the first round, the blue device is active, then the meta model will be pulled towards to the local minimal of the blue device, because only the blue device is active. And then in the next round, the orange device is active, and the meta model will be updated towards the local minimal of the orange device. And then same for the purple device, same for the brown one, and same for the red one. And then the result is that in this case, because each update is towards to the local minimal of devices, and in this case, the meta model will never fall into the global minimal. That is the goal we want to achieve. So we can see that each here and each round, the gradient direction is biased, which means the gradient direction is not towards to the global minimal, but towards to the local minimal. So there exists a gap between them. And in this case, we need to debias the local update. So that is what this paper did.
So yeah, here I have a question. So the bias issue seems like it's because of the client sampling, right? So does that mean that I should not use client sampling during the update? Because you know, if you don't have client sampling, you are always following the true gradient direction, right? The overall gradient direction.
Yes, yes. But even though you don't have client sampling, but usually Federated use like multiple SGD, and if you do multiple SGD, you compute the model updates rather than the gradient. They still exist bias there, right? Because each local SGD go to the minimal, and after if you sum them together, it's not equivalent to the global gradient.
Well, if you want to address that problem, then you can just use distributed SGD.
Yes, yes.
So you don't use the Fed averaging, and you don't use client sampling.
Yes,
yes. Distributed SGD will be able to solve that.
Yeah, I think so.
Okay. So what they want to do, so they say this is a bias, the gradient direction is a bias. So the bias, results from two things. First one is the local update. Another one is the client sampling. Is that what they claim?
Yeah.
Okay. I see. Okay.
So this is the bias they define here, and their goal is to try to mitigate these bias during the local update. And as we can observe that if at each update, we can update our meta model towards our global minimal, that will be good, right? So in the literature, they either you modify the local update rule or you modify the global aggregation rule. So here they modify the local update rule by modify the local objective functions. So the original local objective function is this, which is the loss of the personalized model. And then they add these three regularization term here to try to correct the direction of the original local gradient towards more to the global gradient. So they use the previous global gradient and the previous local gradient and the previous meta model to kind of represent the direction of global minimal. So in this case, by doing so, each local update can be pulled a little bit towards the global minimal. So if we use this kind of local loss at the beginning, they made the local update, for example, the local update of the blue device, which is active, may still towards to the local minimal, because at this stage, the global minimal is unclear. The meta model haven't learned enough knowledge from the devices. So at the beginning stage, each local update may still towards to the local minimal, and still towards minimal. And then when the meta model has learned enough knowledge from all the data, it has the global minimal could be more clear. And at this stage, when the local update will be pulled towards to the global minimal. So this is towards to the local minimal, and this one has been corrected. And so on. If we continue this training, this will finally converge at the global optimal. So this is the basic idea of this paper. That is to modify the local object function so that the local gradient can be pulled more to the global gradient. So,
but if you can you go back to but when you want to regulate, for example, you want to minimize this local loss, you have a GT here. The GT
is the average of GIT.
But how can you know the average of GIT? For example, for device I, how can I know your GJ, right?
Yeah, so I'm going to go to more details about how they propose this local objective function.
Oh, okay.
So the ideally the goal is that if we can pull the update towards global optimal, that will be good, right? So ideally, if we assume we know the optimal solution W star, but is unknown in practice, right? You assume we know that if we modify the local objective as this one, and then we take the gradient of this one, we can we just minimize this one, we can find the optimal solution of the W. Here is exactly the W star, which is exactly the global optimal. So by doing so, if we know the global optimal, and then we modify the local update, local objective function as this, we can compute the optimal solution, but we don't know, right? So in this case, they propose a surrogate one, which is to replace the global optimal with the model and previous round. So in this case, they use the previous meta model to replace the global one. And hopefully in this case, each local update can still towards along the direction of current global model. So this, but in this case, they have a problem, is that they are afraid of that the local update is pulled too much towards the global optimal, because the global WT can be a stationary if the WT is a stationary point of the local objective, and then the local update will be stuck at this point. So then they want to they want to add more directions over this the previous model. So here they want to add more directions, which is the direction of other devices, the direction on other devices. In this case, the local update will not stuck at a stationary point and got more chance to go to the real global minimal. But here we can see that we can compute because this is on device I, and it's easy to obtain the global model, a previous global model. So this gradient can be obtained. But for this gradient, because device I does know the gradient of other devices, so it needs the server to compute this gradient, so to server to collect this gradient from other devices and send this average gradient to each device. So in this case, the server needs to first compute its update its meta model, and then second to compute this average gradient. So in this case, at each communication round, the server needs to transmit two models. That is, one is the meta model, one is the average gradient. So this increased the communication cost to 2 times.
So, so during the interaction, so before each device just download, so the server send the global model to each device, then each device just update and send the updated model to the server. That's one round, right?
Yes, yes.
So now each device, now the server first send the global model WT to each device. Then each device need to calculate their gradient, like this one, right? The Fi, Tj, this gradient information, and then send it to the server.
Yeah.
Then server aggregate them, then they will just send this aggregated gradient back to each device. Then each device will solve this optimization problem to get the model update.
Yes.
Right? So it's basically like each round consists of 4 interactions, right? So download, upload, download, upload.
Yes, but yes, ideally to solve this problem, yes, it is. But they want to kind of save the communication cost. They use kind of if we use T, here we use WT minus 1, then each device can compute this gradient and this at the same time and transmit these two at one round.
Well,
but still the communication cost is
yeah.
the same.
Do they have for example, the workflow, the algorithm workflow, saying that what kind of information are transferred between different parties in the paper? Because it looks like seems that they need two rounds of communication. No matter what you do, because
yes.
transmit the model and the gradient.
Yes, yes. Theoretically, they need 2 rounds of communication, but they approximate this one using previous gradient.
Yeah.
On the server.
You mean they just so using previous gradient? Using previous gradient, do you mean that they're actually using for example, replace WT by WT minus 1?
Yeah, kind of. Yes, that's the previous gradient.
Yeah, but for the previous gradient, we still need 2 rounds of communication, or 2 rounds of communication to calculate the previous gradient, right? So you can say that no,
they use previous local gradient, like previous local update to approximate this value on the server. They do not exactly compute the gradient of WT, but still they need to transmit 2 models per round. So you can compare. So then they propose another surrogate solution, which is in this one they only need to transfer 1 model, because they replace the WT, the global one, with the local WIT. Here they replace the WT here, and in this case, this can be obtained locally, and this can be derived from the WT locally and on I. So in this case, the server only needs to transfer the WT to the device, and the device can obtain this is its previous gradient, and device can derive this gradient from the WT.
How can they derive? For example, for this formulation, how can they derive this one based on this WT?
Yeah, they are kind of use approximation to approximate this value. So they don't actually use the gradient. Actually, they use model update. So it's easy to compute, right? So the sum of model update will be WT minus 1. So that's why this can be derived by WT, but and this formulation, this cannot be derived from WT.
So yeah. Can you go back? Can you go to the this one? So this one, but if this one, for example, if this one is the WT minus 1, if this term is WT minus 1, then this one actually should give you, this one actually is WT minus 1, right? This is this overall term.
Yes.
Because this is the total model update, right? Assuming that everyone just follow this step, you get this one.
Yes.
Now you replace this WT minus 1 as WJT. I feel that it looks like it's still weird,
But how about if you think it's a, distributed SGD with client sampling? So the sum of all the gradients will be the model update gap, the model difference. So as long as you have WT and WT minus 1, you can compute this term, the third term.
I think there should be some kind of serial to support this, right? They should have some, for example, equations trying to prove, well, the optimal solution will be looked in this form. Yeah, I assume this is the ICML paper. They should have such kind of.
Yeah, I understand what you are looking for, but their logic is like they start from the ideal one and then provide a surrogate and then provide a surrogate.
So yeah. So for example, equation 2, right? If you directly implement this equation 2, then it will be 2 rounds. It's not 2 rounds. There is 2. Each device need to communicate with server twice in each round, right?
Yes.
So if you directly implement this one, so they say, well, this is the communication cost is still too high, right? So they go to the. Can you go to the next slide? So go to this one. Then they say, well, this one we only need to communicate once, right?
Yes.
Then there should be some kind of the formulation. There's some kind of equation derivation that you can prove. It's not very obvious to me. I'm not sure. Yeah, I don't know what do they say or say.
You mean some kind of proof derivation, like the bound on the update or something like that? I saw the similar thing in other papers that provide a different local update rule.
I know.
But they
provide, but yeah, they make it. I think they are not the first one to do this. Okay, I think I remember some other papers may have done this before as well.
Yes.
But I just because I didn't read their papers carefully, so I don't. I still don't know why they can do this, and by doing this, why? By doing this, so. Even I say, okay, this is an approximation to the previous equation 3 is approximation to the previous equation, that's fine. I think I can get that. But for under equation 3, why this can save communication wrong? That's what I want to figure out. So even for this one, for example, looks to me, because you still need to get J, the information from device J. So it looks like this is still the device need to communicate with server twice as well.
Okay, I got your point. I think we can later we can go through the algorithm in the paper where they state how they can calculate this kind of gradient. Is that okay?
Okay. That's sure.
So so they also gave the convergence analysis, and the result is that to achieve a target arrow epsilon, the number of needed communication round T is linear to 1 over the arrow for both convex and non-convex loss functions, which is pretty good compared with traditional Federated algorithms. And compared with the state of art, which is the work proposed by the FOLA, they do not have assumptions on the heterogeneous levels. So in the experiments, they evaluate their method over 3 different data sets, the CIFAR-10, CIFAR-100, and the mini ImageLab. And there have 100 devices, and each communication round, 10% of the devices will participate in the training, and they fix the total number of communication rounds as 1,000. And to generate a heterogeneous data set, they force each device only have a subset of classes. For example, device 1 has classes 0 to 4, and device 6 has classes 5 to 9. And they further flip the label indices to achieve some kind of to protect the privacy of the label, because different devices have different labels. And in the results, they report the local testing accuracy and also the communication cost compared to achieve a target accuracy compared with some baselines. So before we go to the details of this image, let's introduce what are the algorithms they used here. So here we can see there are 1 to 6 algorithms, and this one is the state of art done by FOLA, and this one is also to solve the personalized feature learning. And we can see there are 2 types of like the proto and the ML. So the proto and ML represent different adaptation functions, FI, that are used to convert the meta model to a personalized one. And the Diane and the scarf, ignore the PFL. The Diane and scarf are 2 different algorithms like fit average, but these algorithms are designed to correct the bias or the drift of local updates in federated learning. So their goal is to solve the federated learning problem, not the personalized learning problem. And the PFF Diane and the PFF scarf the proposed algorithm of this paper that improved the Diane and the scarf algorithm. So specifically, the PFF Diane improved the Diane algorithm using the local objective function 3. That's the last function proposed by this work, and to achieve the personalized federated learning. And the PFF scarf is modify the scarf algorithm using the local objective function 2 proposed by this work to achieve a personalized federated learning. So as we talked before, the objective function 3, the last one, they only need to transmit 1 model per round, and but for the function 2, they need to transmit 2 models per round. And for the startup art, they use the MAML adaptation function to adapt the meta model, and they use the filter average algorithm to solve the personalized federated learning. And the P average proto here is same to this algorithm, the step art, but they used the proto adaptation function rather than the MAML adaptation function. So this is all the algorithms they show here. and the algorithm named with PFL are their own the proposed algorithms. And then they report the average text accuracy, which is the average of local text accuracy with respect to the number of model transmitted. So for all the algorithms except the PFL scarf, which use the function 2 as the local objective function, the number of model transmitted equals to the number of communication rounds. But for the PFL scarf case, and each round they need to transmit 2 models, then the number of model transmitted will be 2 times the number of communication rounds it has. So these results are reported over the dataset CFAR 100 with flipped label indices and 5 classes per device. Here we can see that the algorithm that achieved the highest testing accuracy is the PFL Diane with proto adaptation, because proto adaptation works better than the ML adaptation when the data are super heterogeneous. And then the second one is the PFL scarf proto. It's still with proto adaptation function, but it's use the second objective function, which needs 2 models to be transmitted per round. And then the third one is the P average, which use fit average to solve the problem and using a proto adaptation function. And then is the last 3 is the algorithms with ML adaptation functions. We can see that the proto adaptation functions works much better than the ML adaptive functions, and the worst is the baseline, which use fit average to solve the problem, and with the ML adaptation functions. So in conclusion is that the PFL, no matter is modified or based on Diane or scarf, performs converges better than the baseline. And then they also report the relative communication cost with respect to different heterogeneous level. So the relative communication cost, that is the number of model transmissions relative to 1 round of failures work required to reach the target testing accuracy. So we can see that all the algorithms, like the orange one, the purple one, all the algorithms with ML adaptation needs a lot of communication rounds or communication costs. But if we use the proto adaptation, it works better. And compared with the P average, which is the baseline that use fit average with proto adaptation, their method PFL Diane can perform a little bit better than the baseline here. So as the heterogeneity level increase along this direction, so increase this difference, the gap becomes larger, so the savings increases. And finally, they also report the relative communication cost saving over different data set. We can observe that the high communication savings across different data sets still exist. So any problem for the experiments?
I have some questions related to experiments. Could you go to the experiment setting?
Mm-hmm. This one?
Yeah, here. Like for I know, like when you want to simulated federated setting, you should just like you mentioned here, device 1 has classes, like 5 classes, device 6 has some classes here. And I know you randomly gave some classes to each devices. But my question here, what's the last point means further flip label in indices? What this mean?
Oh, that means because if each device have different classes, so it doesn't matter what's the index for this class is right. So they permute the labels index. But they claim why they do so is to achieve kind of heterogeneous, and more importantly, they want to keep the privacy from the privacy of the label to achieve some kind of anonymity here.
Sorry, I don't understand, but like my question is my confusion is like based on what you said, is flip the label index should be the picture is a cat, and I just randomly gave it the label is a dog. Is this case?
It's not. Yeah, it's not going to change the label of the cat. But if the label of the image is cat, and you need to use a index like 1 or 2 to index the cat, right?
Oh yes. So yes. So you want to randomly shuffling the local device data?
Yes.
What this will help no, I want to say when you go to when you training this algorithm, you use SGD, right? You sampling that random sampling. So what's the difference between that random sampling and here flip the label indices?
Okay, so the difference is that I think what they do is if your the cat is indexed by 1 and dog is indexed by 2, and the pig is indexed by 3, and they flip the label index. In this case, the cat is indexed by 3 randomly. The dog is indexed by 2, and the pig is indexed by 1 in this case.
Yeah. So
do you
what
mean
is important? I mean, yeah. So go ahead.
Yeah. I was thinking that mean that they are, for example, different device. They have different label space. For example, they use different names or different numbers to represent the same label. For example, we're talking about the cat, but I'm using 1 to represent the cat. You are using 3 to represent the cat.
Okay. Oh, they redefine like a 0, 1, 2, 3, and what the meaning, what the real meaning. Maybe the 0 in this device means cat, other 0 in other devices means dog, right? That's it.
Yeah, they want to permute that. They say their motivation is stem from the practical privacy concern. For example, if this device only have cat, dog, and maybe someone can infer that it only has cat and dog from the model parameter or something. So they further permute the index, not of the class.
Okay, I see. Okay, could you go to your slides? Next page. Here, my question is you mentioned why the proto the proto is the adaptation function, right? Adaptive function, and it's better than MAML.
Why it's better? So
yeah, look like you see compare the result, right? All the proto adaptation function is better than MAML.
Yes. So this depends on how the proto and ML works. So I can go to additional slides here. So for the MAML, this is the meta model, And ML adaptation is to update this meta model by one step of the SGD. So this whole thing is the new personalized model. So this is how ML works, adaptation works. And then for the proto adaptation, the proto adaptation works like something like the like a non-parameter algorithm. Is like in the proto transformation, it will construct the class representation using the meta model and the data on device. Basically, it's first of all, when the device I received the meta model W, it will use that model to compute a representation for each local data point. So you get rid of the several final layers. Just use the model to compute a representation, and then you compute the average of these representations for each different class. So for class K, you got a average representation, and for another class, you got a different representation. And then how do you use this average representation for class K to determine the label of test data? So it's based on the distance of this average class representation and the representation of test data. So they got the label of the minimal distance.
Oh, so that means like you get a K here. That means you want to find like for X is a feature. You want to find the label, right?
Yeah, you want to find the label. If
kind of prediction, right?
Yes. So in this case, you can see that the proto is more. Sometimes if your class distribution is really heterogeneous, then proto adaptation may works better than ML, right? Because it directly depends on your distance between your class representation and your test data's representation.
Yes, I see. Okay. Okay. Oh, could you also go to the experiment? Yeah, like in the next the 11. Yeah, here one. What's the relative communication cost here means? Like there is a baseline for them, like
yeah,
I don't understand the number here and why some MAML is so high and the proto is so low.
Okay, so that is so first of all these results are given a target testing accuracy, and they run the algorithm for many communication rounds until they reach the target accuracy, and then they can then collect how many rounds each algorithm used for reach this target testing accuracy. So all these results has achieve the same testing accuracy, and then as I said, every algorithm will has their number of rounds to achieve this accuracy, and then the relative communication cost is to compute the number of model transmissions over of this algorithm over the number of model transmissions of the baseline, which is the FOLA. So that is the ratio between all the other algorithms and the state of art. And because we can see that I think it's SCARF, it needs one model transmission per round. So that's why they compute the number of model transmissions over the baseline, not the number of communication rounds here.
Okay, I see. But you see the purple one is the same as the black one, the baseline. So why? There's no advantage like for
Yes.
when you use scaffold MAML adaptation function. What's the reason for that?
So the state of art here, they also use MAM adaptation. So MAM adaptation works not well, right? And and the difference here is that this baseline they use the fed average algorithm, but this algorithm they use the scarf algorithm, and also they use the proposed local objective function. So compared with the state of art, it has two advantages, but the scarf needs two rounds of needs two model transmissions per round. So even though it has advantages over this one, the communication cost is high. So I think that's why they finally, to achieve the same test accuracy, their communication cost does not have much difference.
Okay, I see. I see. And okay, and I have another question. Like, could you explain why? Oh, I see. There is oh, I see. I understand the point. Like, could you go to the theoretical result for the convergence?
This one?
Yeah, here. Could you explain like why like this the specific property for this result? I mean, it's personalized to the personalization federal learning instead of another federal average or like the common federal learning. Like I don't know why there's a union point or like the advantage to introduce a personalization adaptation function or the disadvantage of introduce the personalized adapt function. So it will affect some of the convergence rate, right? I mean, how this like a result of how this like the effect of personalization affect the convergence result.
Okay, you mean how the personalization
effect? Yeah.
Okay.
They have some like a unique point compared with the like scaffold or like a federated division, right? Something.
But yes, they do. So from the exact convergence arrow they have in their paper, they do like the choice of local objective function do have influence on your convergence result. But here they just show the big O result, so they ignore the the influence of a specific local objective function like this. But they in their paper they do mention the how the personalization have impacts on the convergence result.
Okay, I see. But another question is like, what does this convergence mean for personalization problem? Because personalization, you only care about the local testing accuracy for each given devices. Like, what does this mean?
Oh, what?
Like, what this convergence result like mean for personalization problem? Okay. Because it's a different problem like for the general federal learning, right? Because like general federal learning maybe care about there is a testing data in centralized model, the average of all testing local data, I mean the union of all local data set, the loss, right? All local data set, I mean, and also centralized something. So, but like for personalization, like why the convergence is meaningful here?
I think
because as you mentioned in the motivation, right? Like the personalization means like the device one try to want to predict the cat, the other one try to predict a dog or like a car or something different. So why this how this difference between the personalization problem with the general federal learning problem, and how this difference affect to the convergence? I mean, yeah, that's I'm confusing. a lot?
I think if you use the like fit average, and in practice they have assumptions on IID data, right? So only on IID they have such assumptions.
No, they don't have this. All the assumptions they show for federal average, non-IID, like partial participation and also like communication cost something, a lot of energy as you want. For generate the federal average.
If you want to get a good convergence result, you need to have assumptions on the heterogeneous level, right? Either is IID or either is bounded heterogeneity.
Yes, we should do that.
Yeah. So then you have, under these assumptions, you can get a theoretical bound on the convergence, right? But here,
yeah.
if you do the personalization is harder to achieve, because in practice, your data cannot fit in the assumptions you made on the heterogeneity, right?
Yes.
If your data is not satisfy that heterogeneous bound, then it's hard. If you still use fit average, there is no guarantee that you will converge.
Yes.
So it's hard to achieve high performance over very heterogeneous data. So that's why they propose the personalized further learning, which is, for example, here they can get rid of the assumptions on the heterogeneity bound, right?
What's doing here is like to deal with the heterogeneous problem, we can just use personalization for the learning, right? That's your your point.
I'd like to say, to deal with the heterogeneity, also other algorithms like the SCARF and the Dian, they are also designed to mitigate the heterogeneity problem.
Yes, but in their theoretical result for the convergence result is like this disparity bound, like there is a heterogeneous bound.
Yeah, but they still have a bound on that, assumption on that. But here you don't have assumption. As if your data cannot satisfy that heterogeneous bound assumption, then you can use this algorithm which do not require a heterogeneity bound assumption, right?
Oh, so okay. So finally, the question is the personalization file learning or personalization adaptation function something is a way to deal with the heterogeneous problem in file learning.
Yes, kind of.
Okay, I see. Thank you.
You're welcome.